Hello and what's up to you all, Premature Killers. It is a lovely Tuesday. I hope you guys are all well prepared to learn more and learn extra with us. Share with me how was your day at school, because I'd love to hear that. And also, if you have some questions on today's show, feel free to throw them at me and Dinyuko, and we'll surely help you. By the way, we also have a team of mindsetters on the page that will help you, because we are a team that likes to help each other. Dinyuko,
Abshen, but
Minjan. Mfukile ngwena minjani?
Nifukile,
Isona itakela kuvona bhuti.
Isona nikona la and niyakujoniseni physical sciences abatshami kahle batshamiseka baba right bayingisela. It's a good lesson in physics, or actually chemistry. We're talking gases. We're continuing with that very story we started.
Isona. Well,
yeah.
mindsetters, to join us on this lovely lesson, all you need to do is to go to facebook.com/learnextra, like the page, share the page with all your friends, and tell even your community to be part of our big community, which has over 77,000 likes. And on Twitter, you can follow us at learnextra. Remember, we still have a competition whereby we're giving away this awesome Casio calculator. All you need to do is to answer the test yourself questions, get them correctly, and all of them correctly, and you could be one of our winners. Last week winner will be announced on the show. Yinko.
You can see it, but let me just take it right away. And today we're talking about, we're continuing talking about gas laws, of course, and we're going to look at another special law, which is called the Gay-Lussac law. So in this lesson, we're going to explain that. We are going to deduce or actually work out the combined gas equation. We are also going to look at what is meant by this STP, standard temperature and pressure, and molar volume. So we're going to be talking about those things of the gas here. We are also going to look at how we work out and explain the ideal gas equation. So those are the things that we'll be doing in this lesson here. Now, check carefully. I'm coming to you with your challenge question for today. Have a look at it. It says, a gas occupies a volume of 300 cubic centimeters at a pressure of 130 kilopascals and a temperature of 20 degrees Celsius. What volume will the gas occupy at STP? So you need to know what is meant by STP. You are expected to work out the volume that will be occupied by this gas when it is under standard temperature and pressure. Okay, now moving on. Let's come to the notes for the day. The Gay-Lussac law, okay? The Gay-Lussac law states that pressure of a fixed amount of gas is directly proportional, so this is very important, directly proportional to absolute temperature, okay? Absolute temperature, provided the volume is kept constant, all right? So when you keep the volume constant and you keep the amount of the gas constant, you would have a relationship such that your pressure, the pressure of the gas, will be directly proportional to the absolute temperature, which is the Kelvin temperature. Once we talk absolute temperature, please understand that we're talking about the Kelvin temperature. We're not talking about the degree Celsius scale of measuring temperature. We're talking about the Kelvin scale of measuring temperature. Okay, now moving on. When a fixed amount of gas is heated under constant volume, so you keep volume constant, the average kinetic energy of the molecules of the gas increases, okay? We know basically that temperature of a gas is actually given by the average kinetic energy of the gas molecules. So when you heat the gas molecules, the temperature of the gas is going to increase, okay? As a result, there are more collisions, okay? So we've got more collisions between the gas molecules or gas particles, as well as between the side of the container and the gas particles. The pressure of the gas on the walls of the container, which is defined as the force per unit area, would also increase. So that will also increase. Now, this would mean, because we are saying that the pressure will be directly proportional to the temperature, that this would mean that we're going to have a graph that of pressure versus absolute temperature, which will be a straight line passing through the origin, showing that pressure is directly proportional to the temperature. This relationship can be shown mathematically. So if we want to show that mathematically, is that pressure is directly proportional to temperature. Okay? Now, pressure is directly proportional to temperature. If we multiply this relationship here by a constant K, what we're going to get is that P will be equal to KT. Therefore, if P is equal to KT, I can have P over T giving me K. Because out of here, if I want to make K the subject of the formula, P over T will be equal to K. So P over T is the gradient of this pressure versus temperature graph. And therefore, it is a constant at any point along that graph. We know that a gradient of a straight line remains the same throughout that line. Okay, so if P over T is the gradient, it will be the same throughout, because here we've got a straight line graph passing through the origin. So we've got a constant, which is that K, at any point throughout that graph. So if that is the case, that will mean that P over T, all right, it's a constant at any point. So P1 over T1 will be equal to P2 over T2. That's what it would mean. Now, moving on with the notes here, let's look at the combined gas equation. The combined gas equation is also known as the general gas equation. To arrive at this general gas equation, we make use of Boyle's law, and we make use of the Gay-Lussac law. Okay. From Boyle's law, we know that pressure is directly proportional to, pressure is inversely proportional to volume. So P inversely proportional to volume up to that point here. And from Gay-Lussac, we know that pressure is directly proportional to T. All right. When we combine the two, we can therefore say that P, or the pressure, is directly proportional to T over V. When the proportionality is multiplied by a constant K, all right, what do we get? We get that P equals, so this is very crucial, we get this one here that says P equals T over V, okay, P equals T over Vk. Therefore, if P is equal to T over Vk, then PV over T will be equal to K, which is the constant, PV over T. So now if PV over T is equal to K, what would this mean if we look at different conditions of a gas? The same amount of gas, we place it in one set of conditions of temperature, pressure, and volume. We remove it, we place it in another set of conditions. What will that mean? It would mean that when we have this P1 V1 over T, which is the first condition, this first condition here will be equal to the second condition here, which is P2 times V2 divided by T2. And when we have that, this is now called the general gas equation. Okay? Don't forget it. Let me rewrite it for you so you can remember it, or you can see it properly. That is the first set of conditions. Okay? Pressure 1, volume 1, temperature 1. You take the same gas to the second set of conditions. So it will be P2 V2 over T2. This should be equal, or those two conditions should be equal. And we call this the general gas law. Okay? General gas law. Okay, so that is basically what we have. Now, quickly, I want to take you through this thing that talks to something called molar volume. Now, molar volume, you would actually deduce from the term itself that when we're talking about a molar volume, it will be a volume occupied by 1 mole of a gas. A volume occupied by 1 mole of a gas. So we call that molar volume, 1 mole of a gas. That will be the molar volume. So this has been found experimentally that 1 mole of any given mass of a gas will occupy a volume of 22,4 cubic centimeters. So that 22,4 cubic decimeters when we have what we call standard temperature and pressure. And this is what I meant at the beginning when we were talking about, when I said I'm going to introduce to you the STP thing, standard temperature and pressure. A temperature of 0 degrees Celsius, which is actually 273 Kelvin, and a pressure of 101.3 kilopascals are the STP values. These are your standard temperature and pressure. Thus, the number of moles occupying a particular volume at STP can be found by using this formula. If 1 mole will occupy a specific molar volume, okay, number of moles, we can find it by looking at how much volume is occupied by that gas divided by the molar volume. Okay, so which is 22,4. That equation becomes very important. So you need to know that. Where we know that N is the number of moles of the gas and V is the volume occupied by the gas. And very important, MV is the molar volume of the gas at STP, which is constant, which is always equal to 22,4 cubic decimeters. You must be reminded, though, that if the quantity of the gas at STP is given in mass, all right, if it is given to you in mass, so much of the gas in grams this time, how are you going to work out some of these problems here? You would need to know that the number of moles from that given mass can be found using the formula number of moles equals to given mass divided by the molar mass, capital letter M for molar mass. Like I said earlier on, N represents the number of moles. This time we've got small letter m there. The small letter m represents the given mass of the gas. All right, so given mass of the gas. And capital letter M, very important. Capital letter M represents the molar mass of the given gas. Okay, so differentiate between the two m's, small m, given mass. Capital letter M, molar mass. Okay, for example, if I want to get the molar mass of oxygen, I would say the molar mass of oxygen will be equal to 2 times. Every atom of oxygen has got 16 grams, so 2 times 16 will be equal to 32, and we will say this is 32 grams per mole. So that is what we call the molar mass. So if you are to find the molar mass of a certain gas, in this case, because we're talking gases, of course we can use it for any other situation, maybe looking for calcium carbonate, it's a solid, want the molar mass of that, you can use the same equation. But for now, we're talking gases. So for any gas that is given to you, if the quantity is given to you in mass, grams, you can work out the number of moles making use of this equation, making use of this equation, and also knowing that if you are to get, if you're not given the molar mass, you are to work it out. This is the way to work it out. And I think we're going to work out something like that in this lesson as we proceed. Let me give it back to Abram for now.
Into support kufanelekile hiye emavengeleni.
Hayi emavengeleni shabisa.
But before hiye emavengeleni, I've got these two shout outs from Vele, Vele Mufunwa Denga. Big shout out to you, Vere. Vere, yeah, because I think it's Vene, it's Vere.
Vele, Vele.
Oh,
Is
Vele.
it V-E-L-E?
Yeah.
Okay, it's
But
Vele.
I think that's how they pronounce it.
Vele. Yeah.
Okay, Vele,
Yeah.
a big shout out to you. And also Shikash in the jet, a big shout out to you too. He was a former mindsetter, but he's watching even today. So thank you guys. We'll check you out after the break. Welcome back, awesome mindsetters. Now, the moment we've all been waiting for to hear our winner of this Casio calculator. Well, because I've been, speaking a lot of Tonga earlier on, the
Yeah.
mama and Velen Tetis course,
Uyothetha ngoku.
yeah, man, Tetis course. Tinyuka's gonna tell us who's our winner because I feel like I should also make him part of what I'm doing. So, who's our winner?
Okay, listen to me carefully. Here is the winner of the fabulous Casio calculator to do all your science and mathematical calculation. And that is Asakundwi Munjedzi. Thank
Nice
you.
one. Asakundwi, congratulations to you.
Munjedzi, yes.
And mindsetters, you could be like a helm. All you need to do is to just do the test yourself questions and stand a chance of winning this awesome Casio calculator. Kodwa-ke kwangoku ixesha liqhatshwe yinja, masihlabele mgama with our lesson.
All right, thank you. I think I heard what you said, but then let's proceed here and takes care of the time that Abraham mentioned in his statement. Now, let's proceed. Let's look at the questions now. Question 1, all right? In the notes that you're going to receive and download from the Mindset web page, there is more notes on what I had. The notes, the latter part of the notes will be talking about the ideal gas equation, okay, which will be necessary for you to know. A certain mass of carbon dioxide gas is sealed in a 200 cubic centimeter container. The gas exerts a pressure of 100 kilopascals on the sides of the container at a temperature of 0 degrees Celsius. Now, calculate. Calculate. Number A, the number of carbon dioxide gas moles present in the container. Number of moles of the carbon dioxide gas present in the container. Now, if you check on what is given to us, let me just list them on the side here. We are given the volume in which the gas is kept. The volume is 200 cubic centimeters. And we are also given the pressure that the gas is at. So pressure is 100 kilopascals. All right? We are also given the temperature in which the gas is kept. Okay? We are told that this is at a temperature of 0 degrees Celsius. Now remember that we don't use the degree Celsius scale, we use the Kelvin scale. So from 0 degrees, converting, you always add 273, and that gives you the Kelvin. So you've got 273 Kelvin. All right, so that is your temperature. Okay, now, number A, we are to calculate the number of moles present in the container, given all those information. Now, A, if you look at the information given to you, the equation you are to use will be the universal gas equation, PV equals nRT. Why am I using that? Because I am given the pressure, given the volume occupied by the gas. I need to find out how much of the gas is there, and that is given to me. It's a constant, and that is also given to me. All right. Now, also, when I use this equation here, or this formula here, I need to know that always the pressure is measured in pascals. This is the SI unit of pressure. The volume has to be in cubic meters. That's very necessary for me to know. Of course, N should be in mole, okay, measured in moles. And R is the universal gas constant, which is always known to be 8.31 joules per Kelvin per mole, okay, per mole. Allow me to write like that because I don't have much space. And the temperature must always be in Kelvin, okay. So this is very important. Why do I say so? Let's come back here. You will see that you are given volume in cubic centimeters. You have to convert. You are given pressure in kilopascals. You have to convert to pascals. So let's work it out. 100 pascals, kilopascals in pascals, you need to multiply by 10 to the 3 so that you come back to pascals. Then multiplied by volume, you have got 200 cubic centimeters to cubic meters. Because if I move from cubic centimeters to cubic decimeters, I'll divide by 1,000. If I therefore move from cubic centimeters to cubic meters, I'll have to divide by 1,000,000. That is 10 to the 6. So it means this 200 cubic centimeters is 200 divided by 1,000,000, which is the same as multiplying by 10 to the power minus 6. This must be equal to my N, is what I'm looking for. R is 8.31. What is my temperature? Times the temperature, which is, if the temperature is 0 degrees Celsius, it will be 273 Kelvin. Okay, so you work this out. Let's just work it out. Where is our calculator? So I've got here 100 times 10 to the 3 times 200 by 10 to the power minus 6. Okay, what does that work out to? It works out to just 20. So all this in the left works out to 20. And the right-hand side, I can simplify it. You have got N times, okay? So N times what? You've got here 831 times 273, okay? So 8.31 times 273, the Kelvin temperature. You have got 2268.63, 2268.63, okay, comma 63. Now, the number of moles equals, all right, so that will be equal to 20 divided by this, okay, so 20 divided by 2268.63. And what is that? That gives us 8.82 by 10 to the power minus 3. 8.82 by 10 to the power minus 3. Okay, what is this? This is moles. Okay, this is moles. So I have found now the number of moles present in that container. Let's come to number B and see what number B wants us to do. Now, number B says, calculate the mass of the carbon dioxide gas in the container. Now, for me to get the mass, what am I going to do? Now, I have the number of moles of the gas now from the gas equation. I need to move to the mass. To move to the mass, the equation or the formula that helps me to get the mass is this one. That says number of moles is equal to given mass divided by molar mass. Okay? So this equation here would help me because I am going to substitute this value for the number of moles. And I need to know what is the molar mass of this gas. Now, the molar mass of the gas, let's work it out on the side. Remember that I said if you are to work out the molar mass, you will have to look at the gas, and that will be equal to, for carbon, you look at your periodic table, you get the molar masses from there, the masses of each atom that is involved in that particular substance. For this substance here, we've got carbon dioxide, CO2. For carbon, you check your periodic table, it is 12. For oxygen, you check your periodic table, it is 16. So you work it out, this is 12 plus 2 times 16 is 32. This gives you 44. Now, this is the molar mass of carbon. So it's 44 grams per mole. For every mole of carbon, we will have a mass of 44 grams. That's what it means. Therefore, coming back here and finishing off my calculation, I will then substitute the number of moles here with what I calculated here. It's 8.82, 8.82, so 0.82 times 10 to the power minus 3 will be equal to, mass is what I'm looking for. Molar mass I have calculated is 44. So what does this mean? Therefore, the mass of carbon will be equal to 44 times 8.82 by 10 to the power 3. So let's go there. I still have that value there. I'll just say multiply by 44. Okay, multiply by 44. And what do I get? 0.39 grams. 0.39 grams. So that is the mass of carbon that I have. Okay, I mean of carbon dioxide that I have in that container. Right, going back to the next question. Okay, question number 2. Question number 2 says, a certain gas at a temperature of 20 degrees Celsius and a pressure of 80 kilopascals is kept at or is kept in a container of 250 cubic centimeters. The gas is now compressed such that its pressure decreases. Okay, oh, this should have, let me just change it for you now. Bit of a mistake here. Pardon me for that. So it is compressed. It can't be compressed from 80 kilopascals then to 130. If it is compressed, that pressure must get less. So compressed to 60 kilopascals. Okay, so remember that. We're going to use that one instead of the 130. The temperature of the gas increases because of what has happened, because of the compression. It increased from 20 degrees Celsius to 45 degrees Celsius. Now, calculate the volume of the gas after it has been compressed. Now, let's look at what is given to us quickly. You've got pressure 1, which is 80 kilopascals. You've got volume 1, which is 250 cubic centimeters. All right? Then you have your temperature 1, which is 298 Kelvin. And that is 20 degrees, I mean, that's 20 plus 273 to give me 298. And then you have the second part here. You are told that it is compressed such that the pressure comes to 60 kilopascals. All right? And then when that happens, the temperature increased from 20 degrees to 45 degrees. Okay? And what is that? That will be 45 plus 273. What do you get? That gives you 318 Kelvin. Okay? And from there, then we can work out our problem. If you look at what you have here, you can actually think of what law you are going to use. Let's just quickly have a look at it. P1 V1 over T1. This is the combined gas equation. Should be equal to P2 V2 over T2. All right. Over T2. So I can begin to substitute here. P1, I've got 80. I've got 80 times. V1 is 250 divided by. T1 is 298 equals. P2 is 60 times. V2 is what I'm looking for, and T2 is 318. Now, come on, you take out your calculators and we work this out together. All right. Now, 80 times 250 divided by 298. What do we get? The answer is 67,11. 67,11 equals. Okay? And then this side, I've got 60 divided by 318. 60 divided by 318. What do I get? I get 0,188. 0,189. Okay, 0,189. 0,189. What is the quantity I'm looking for? Is V2. Therefore, V2 equals 67 divided by 189. 0,189. Okay, so let's work it out here. So 667,11 divided by 0,189. 189. What do I get? Let me do it again. There's a mess here. 67,11 divided by 0,189. And the answer is 355,08. 355,08. So 355,08. Okay. Now, let me check here. Okay. Right. So you have, we need to work this one out quickly. I think there's something that went wrong here. We shouldn't be getting that answer. Anyway, let's go back to it. Let me see. I think I still have some time quickly to work on it. Let's just go back to it. There is something that went wrong somewhere here. So let me just quickly erase this, and then we work it out quickly. Okay. Right. Now, from there, it's 80 times 25 divided by 298. So 80 times 250, not 25, 250 divided by 298. 298, and let me just ascertain that is 67,11. Okay, so 67,11 equals 60 divided by 318. Okay, quickly, 60 divided by 318. 60 divided by 318. What is that? 0,189. 0,189. 0,189 V2. So why are we not getting? Okay, so then this would be equal to V2. Okay, therefore V2 equals 67, comma, okay, let's go back there. 67, comma, 11. We divide that by 0,189. Why do I still? Okay, that's fine. Then it gives us 355, 08. 355,08. Okay, 355, 08. 355,08. This must be cubic centimeters. So that is the way you were supposed to work out this question here. Now, for something for you to always note is to make sure that your Kelvin temperature is the scale that you are using all the time, nothing else. Let's just stop there and we go back to Abram.
Right, I've got a surprise for you, Tinyuko.
Okay.
Do you like surprises?
Yes, let's hear.
Okay, what do you love most between singing, dancing, and acting?
Singing, dancing, acting.
Yeah.
I think I prefer singing more.
Awesome. Okay, cool. Got a surprise for you. My
Okay.
sister, stay tuned. After the break, I'll be telling you guys where we're going.
But don't make me sing. Don't
I
make
want
me
to.
sing.
Welcome back, Mind Sisters. Now, due to the amount of questions that we have for you guys, I feel like we should give you guys more time. And Tinyuko, you're going to sing for your mindsetter just before the end of the show.
Okay.
Because it's someone's birthday. It's Pomelelo Pasha. And she says, hi, TK, I'm enjoying the show. A shout out of my name, and it is my birthday today, and to all the other mindsetters at Bongoni Technical High in Atteridgeville. So, Tinyuko, you're going to sing for
Pasha.
Pomelelo.
No,
Yes.
I'm gonna sing for her.
Later on.
I'll try later on.
But
Yeah.
without any waste of time, the
Okay.
mindsetters have noted a mistake.
Yes, we have actually found it. In fact, the calculation itself was actually making me think, no. That's not the way it should be. But then let's go back to it. Instead of changing this one to 60, the word here should have been saying that the pressure increased to that, because when you are compressing something, the pressure of the gas actually should increase. So that's where I was actually getting it a bit wrong there. So the pressure increased or increases to 130. So 130 stays, and down here, thanks to a mindset that helped us to see it, is it a she, Abram? Somebody.
It's so
a
many of
mindset
them.
that
It's so
helped
many
us
of them.
to see where the mistake is here in our calculation. So you would see here that instead of, when you have 20 degrees Celsius, that will be 293, not 298. I'm used to the 25 degrees Celsius. This is 20, so that should be 293. That side, that stays, but what should change? This must change to 130. Okay, so that is 130. Then when you work out this, it will then begin to make sense, because it will show us that actually the volume has decreased. If you compress something inside a container, the volume of that particular substance is bound to decrease. Okay, so you work this out quickly. We worked it out this side. Let's just go through the calculator quickly. So this is 80 times 250 divided by 293. Okay, and we get 68,256, 68,259, 68,259, and that equals If you go back to our calculator, we work out the fraction this side, which is 130. You divide that by 318. Okay, 318, and your answer is 0.409. 0.409. 0.409. And then you work this out. This is V2. Therefore, V2 would be equal to 68. Okay, it's going to be 68,259 divided by 0.409. You would see that I am very consciously keeping 3 decimal places because I'm not yet down to the answer. So 166,89. 166,89 cubic centimeter. Yes, this volume here makes sense because we are from a volume of 250 cubic centimeters down to a volume of 166,89. Right. Now, moving on, going straight to the challenge question, and I believe we'll be able to attend to most of your questions at the end. Now, the challenge question says a gas occupies a volume of 300 cubic centimeters at the pressure of 130 kilopascals and a temperature of 20 degrees Celsius. What will the gas, what volume will the gas occupy at STP? Now, what are STP values? Pressure of 101.3 kilopascals and a temperature of 0 degrees Celsius, which is 273 Kelvin. All right. Then the other values that are given to us is a volume of, so the first volume, if you like, will be what has been given to us, 300 cubic centimeters. And then we are told at a temperature of, okay, the temperature of, this will be T1, the temperature of, again, 293 Kelvin. That is 20 plus 273, so that's 293 Kelvin. Let me have a good K there for you. Okay, so this will be your T2 because it's the second set of conditions where everything has been, or this gas has been placed under standard temperature and pressure, STP conditions. And then the question is, what will be the volume? So what will V2 be? Now, if you look at all that is given to us here, it immediately suggests to you what formula you're going to use. Actually, you are going to use the formula that we used earlier on, the combined gas equation. P1 times V1 over T1 will be equal to P2 times V2 over T2. All right. Now, what was P1? P1 was 101.3 kilopascals. No, that is standard condition. That should be P2. So what was P1? P1, let's check here, was 130 kilopascals. So P1 is 130 kilopascals. Okay, so we'll say 130 times V1. V1 is 300 cubic centimeters. Okay, divided by temperature 1 is the 293. Okay, 293. That will be equal to pressure 2 is the standard pressure, which is 101.3 kilopascals. Don't have to put the units for now. Then V2 is what I am looking for, and the temperature 2 is the standard temperature, which is 273 73, okay, or what we call 0 degrees, right? Then we can work it out. Pretty much the same like what we have just done, okay? So let's work it out now. Where is our calculator? You've got your 130 times 300 divided by 293, and let's get that value, 133,105. 133,105 will be equal to, okay, this part here will be 101,3 divided by 273. Okay, and what will that be? 0,371 V2. 0,371 V2. And then, therefore, your V2 would be equal to, all right, 133,105 divided by 0,371. 371. Okay, are we there? So that is 358,77. 358,77 cubic centimeters. Okay, so that will be the new volume that has been occupied by the gas. Okay, that will be the new volume, the volume at STP, the volume at standard temperature and pressure, as we were asked. Let's just check questions that the mind setters are having for us today, Abram.
Yeah, so many questions. Let's start with this one. What is meant by the term grams per decimeter cube?
Grams per decimeter cube. Grams per decimeter cube.
That's from STE.
Okay, and grams per decimeter cube, that is, you are dividing mass by volume. So it's mass over volume, if you like. Now, mass over volume may not really help us much in what we are doing now, but if you've got grams per cubic decimeters, it just tells you how much mass are you having in a volume, in 1 cubic decimeter, and that's all. And if you were to come back to what we're dealing with, if it's number of moles that we are talking about, which is perhaps talking standard conditions, okay, where the volume of the gas or the volume occupied by 1 mole of a gas under standard conditions will be 22,4 cubic decimeters. Number of moles will be given by the given volume divided by the molar volume. I think you will remember that. So this will be, you will have volume, you're measuring it in cubic decimeters. Let's put it that way. You're dividing by molar volume, okay? And therefore, it will be mole. What would we have here? So molar volume will actually be mole per volume, or will be mole per cubic decimeters. So this, I mean, molar volume will be in cubic decimeters, so it's mole by cubic decimeters, okay? So that and that is going to cancel, so it will be cubic decimeters, sorry about that, trying to work it out for you here. It will be cubic decimeters divided by cubic decimeters per mole, all right? And therefore that and that cancels out, and that going out gives you the number of moles. So it's just a way of playing around with the units, but this is not that applicable to what we are doing now in terms of the gases and the units of measurement that we are using.
Okay, let's move on. Another question.
Yeah.
In question 1, why did you multiply 200 by 10 to the power minus 6, please?
Oh, okay. Let me explain this. Okay, if I've got cubic centimeters and I am to convert into cubic decimeters. Oh, look at how this thing. So cubic centimeters, conversion to cubic decimeters. What I will do, I will divide by 1,000. Okay? Now, if I am converting from cubic decimeters to cubic meters, I will divide by 1,000 as well. Now, the issue is, I'm not from cubic decimeters to cubic meters, but I am from cubic centimeters to cubic meters. It means I am dividing by that 5,000 and another 1,000. And that means that I should be dividing by 1,000,000. Okay? And dividing by 1,000,000 is the same as multiplying by 10 to the power minus 6, because that is 1, 2, 3, 4, 5, 6, up to that point, okay, to your first significant number. If you're dividing by 1,000, it's the same as multiplying by 10 to the power minus 3. So that is why I had to multiply that 200 by 10 to the power minus 6, because I was converting from cubic centimeters to cubic meters, a much, much bigger unit of measurement compared to cubic centimeters.
Okay, another
Right.
question. Tabos Menya, is it a problem if I make the unknown variable subject of the formula?
Oh, good question. What's the name again?
Tabo.
Tabo, it is not a problem at all. But through our experience as science teachers, we have seen that when people work around finding out the subject of the formula for what they are looking for from a complex formula like this one, okay, this formula is a bit complex. If you try to find, let's say, for example, you're trying to find V2 as we were working out here. So you want to find V2. It's not a problem. You can get it. But in the process, many people would fumble and make mistakes. So what we advising is that rather substitute into the equation as is, because you get marks for what you're doing. Let me go back to this. Let me show you what I'm talking about. So say we mark you. We give you a mark for that formula, and I may give you a mark for that correct substitution, that one, that one, that one, and that one. For all those, it will depend. Sometimes this whole thing could give you 1 mark, but I'm showing you how the marks are distributed. So you get everything there. But suppose you come straight here, Tabo, and you mess up, okay? So you come straight here. So we give you a mark for this one here. But when you come down here, you mess up the whole thing. You're looking for V2, and then you say V2 is equal to P1 V1 divided by T1 times T2 times P2. Okay, then you work it out. Obviously, this makes, because this is wrong at that point there, whatever you're going to substitute here is going to be incorrect. So you have actually wasted all these marks. That tick goes, that one goes, that one goes, that one goes, and that one goes. You have lost about 5 marks gone, lost, because of just a simple mistake of making your V2 the subject and messing up that part there. That's why we are saying substitute into the equation first. So that is always advisable.
Sure, wow. Unfortunately, our time has ran.
It's up now.
So thank you so much, Mr. Tinyuka. Unfortunately, didn't sing for the mindset, but I'll record you after the show and then I'll post it on Facebook.
Okay, so sorry to the lady.
Pumelelo.
Pumelelo, yeah, but happy birthday to you.
Thank you so much, Tinyik. Well, my
Yeah.
teachers, thank you, Akenta, Ralebuwa, Siabulela, Enkosi Kakhulu. We'll see you some other time and really appreciate your time. Up until next time, peace.
You can.